We talked about how to describe an association. So when we look at the scatter plot, how do we describe it? So we talked about form, which meant what? What were basically my two options? Linear, nonlinear, or in very rare cases, if there's really just a random scatter, we just say it's unclear, right? But most of the time, we should see some sort of pattern. So linear, nonlinear. We talked about direction. My two options for that were positive and negative, and that's for both linear and nonlinear. So the direction applies regardless of whether we have a linear association or not. And then we also talked about strength, and so that's where we're going to start today's conversation. So when we talk about correlation, we want to talk about this perception of strength. Okay? So yesterday we were kind of vague. We kind of talked about when we talk about strength, we're looking at how closely do the points follow the form. And we said that we are looking at like it's either strong because it follows really closely. We said we could use those auxiliary terms like moderately strong, moderately weak, or if it's just like really scattered around the form, we say it has a weak association. Okay? Now the problem with just describing it in that manner, okay, when we talk about those general terms, is just like we talked about back in Unit 1, I can make the data say whatever I want it to say. I can describe it how I want to. I can make it look how I want to in the graph by just changing a couple of things. For instance, if I look at these two graphs here, if I asked you guys to describe that association on the left side there, for form, we would say it's linear. Direction would be positive, and strength, like moderately strong, right? So it follows the form pretty well, okay, but just a little bit of scatter. When I look at the second one, so if I look at the right, if I wanted to describe that association, we would say that it is linear, positive, and strong, right? We change our perception of strength based on the two graphs there, right? The one on the right looks stronger than the one on the left. The problem is, those are the same sets of data. It's the exact same scatter plot. The only difference is the scales I chose to use for my X and Y axis. So in this first one, I zoomed in a lot more with my scales. I actually looked at the minimum value, maximum value, and scaled accordingly for my X and Y. So I'm actually looking at the entire distribution as it should be. In this other one, we zoomed way out. So I start at 0 instead of starting at that minimum value. I go all the way to 250, which is way above any of my maximum values. And by doing that, it makes the points look like they're more closely scattered around that original form. And so when I'm looking at that strength, again, there was a little bit of subjectivity we talked about yesterday with that strength. So but the way I make it look can change our perception. And so we want to make sure we have a way around that where we can actually have a quantifiable value associated with that strength. And that's what today's topic is all about. So correlation is our primary focus today. When we measure correlation, we measure the strength and the direction for our linear association. And it is extremely important in those first couple of lines there. Correlation measures strength and direction, but correlation is only meaningful when we have a linear association. So this is kind of like when we talked about z-scores back in the first unit. I can calculate a z-score, a standardized value for anything, right? So I can get that z-score. I can talk about how much or how far above or below the mean I am, right? But that z-score was really only meaningful when it pertained to a normal distribution. Same thing applies here. If I have two quantitative variables, I can always calculate correlation. So regardless of what the form of my association, the form of my relationship is, I can calculate correlation. But if I have a nonlinear association, that correlation value that I calculate will be meaningless. It's not going to measure what I want it to. So it is very important. It's the first thing we talk about, and I really want to stress that, is that this only works when we have a linear association to begin with. The other part of this that's extremely important, and it's going to pop up a lot, when I calculate correlation, I have no units attached. So when I'm working with quantitative variables, we almost always have some sort of units. Inches, pounds, hours, whatever we happen to be measuring. When I convert my values into correlation, we're going to be calculating correlation based on standardized values, based on z-scores. And so as soon as I start calculating z-scores, I strip everything of the units, which means my correlation is just a value, no units applied. And we're going to talk about the formula for correlation here in a little bit so you can see what that looks like. But those are the two probably most important pieces to start off with here. Correlation is only meaningful when we're linear, and it has no units. When we get our correlation coefficient, like we talked about, it tells us the strength and it tells us the direction. So a positive correlation means we have a positive association. A negative correlation means we have a negative association. As far as the strength portion of this, that's what the bottom half of this slide is about. So correlation, another thing to point out here, we use the lowercase letter r to denote correlation. Why they chose R, I have no idea. But that's just the one they chose to utilize for this. So correlation is always going to be a lowercase r. It's a number that goes from -1 to +1. I cannot have a correlation value outside of that range. So -1 and +1 are the absolute extremes. I cannot have a correlation value outside of that. The closer I am to 1, the stronger my association is, as long as it's linear. So if it's close to +1, that means my association is positive, and it means it's extremely strong. So the points follow the form very closely. If my value is closer to -1, then it means we have that negative association, but again, being at that extreme, it tells us that we have a very strong negative association. But again, only applies when we're linear. And then if I have a value that's closer to 0, so a lower correlation value, whether it's positive or negative, the closer I am to 0, the weaker my association is. So now we can calculate an actual value and have a little bit better basis for our strength in terms of whether we're strong, moderately weak, or weak. And it'll also tell us the direction of our association as well. Now the last two pieces here are going to be really important for us to remember as well. This is going to pop up in the homework. It pops up on the quizzes and tests. When I calculate correlation, we talked about yesterday with the scatter plots. We have explanatory and response variables that we have to identify. Now when I create the scatter plot, my explanatory variable is my x. My response variable is my y. But we talked about the fact that there's some instances where that explanatory and response variable are a little bit vague. We don't know exactly which one's which. So there's not a clear, obvious choice for explanatory or a clear, obvious choice for response. And so we could pick either one. When we calculate correlation, it will not matter which variable I assign to x and which variable I assign to y. If one person puts it one way and the other person switches the variables up, when they calculate the correlation value for that association, they're going to get the same number either way. So flipping x and y will not affect correlation at all. You're going to get the same value no matter what. And then the other part of that if I change the units that I was originally measuring in. So if I had a distribution where one of my variables was measuring weight and I had measured in pounds, and then later on I decide I don't want to use pounds, I want to use kilograms instead, again, that unit change will have no effect whatsoever on my correlation coefficient. And the reason goes back to that first thing we talked about. When I calculate correlation, units are meaningless. We strip the units from the calculation, so no matter what I do to my original values, it's not going to change my correlation overall. So correlation remains constant regardless of whether we do either of these two things. Okay? So those are the properties, those are the characteristics of correlation that you need to know. And then based off of that, we can do kind of whatever we need to with these types of problems here. So when we talk about correlation, just to kind of give a visual here, so we've got 6 scatter plots on the right side there, each of which has an associated correlation off to the left. And so based on what we just discussed, based on those properties and characteristics, if I wanted to try to match the correlations to the appropriate graphs here. So if I'm trying to match these up, if I were to look at the correlation of positive 0.9 here, which graph would most likely correspond to that particular correlation value? The bottom left. Why? Yeah, because that's a positive association. It's pretty strong, right? The points follow the form really closely, so it probably has a fairly large correlation coefficient, a value close to positive 1. If I look at the one next to it, though, so if I have a negative 0.99, which one is that most likely going to match up with? Bottom right. So now we're looking at an even stronger association, so the points follow even more closely to the form, negative, and so we get that high correlation value close to negative 1. As I look at the rest of these then, okay, if I wanted to match up the 0.5. So yeah, we want a moderately strong positive association. So if I'm looking at the 4 remaining graphs, the one that probably matches best with that would be that middle left one. So we can see that positive association, not super strong, because the points scatter a little bit more randomly around it, but that's kind of what we'd be looking at there. If we looked at the negative 0.7, so fairly strong negative association. If I'm looking at my remaining 3 graphs, would probably go with that middle right. So we can see the negative association. Pretty strong still. The points follow the form fairly well. So we end up with that correlation value of negative 0.7. And then for my remaining 2, as I look at the 2 last options here, so the negative 0.3 would most likely match up with the top right. We see a little bit more of a negative association there, whereas that top left, we kind of just see random scatter, right? So in that case, we'd have that correlation value closer to 0. Okay? So one of the things that's going to be beneficial for you guys is just understanding those characteristics, understanding those properties, is when I look at a scatter plot. So if I create my scatter plot by hand, I create it on the calculator. If they give me a scatter plot, you being able to estimate that correlation value will help out. So when I'm trying to talk about that perception of strength, what type of correlation value should I expect when I plug this in? Okay, so just kind of getting an idea of what that's supposed to look like, how closely we follow the form, and what those appropriate values would be. Next thing, when we interpret correlation, so here we have a scatter plot showing the relationship between height in inches and free throw percentage for a random sample of 20 WNBA players. for these data, when we calculate the correlation value, we get negative 0.427, and they want us to interpret that value for correlation for R. So as we look at this, okay, when they give us a correlation value, the first thing, if I give a correlation value, I also should have a graph representing the association. And why do I want that graph? Why don't I want to make conclusions based only on a correlation value? When's the only time correlation is meaningful? When it's linear. Now, if they just give me a correlation value, okay, I can calculate correlation for anything. So if they give me a correlation value with nothing else supporting it, I can't guarantee, even if it's a correlation value very close to 1 or very close to -1, that doesn't guarantee that I have a linear association. And so if I can't verify that the association is linear to begin with, then that correlation value is meaningless to me. So as we look at this relationship between height and free throw percentage, we do see that it has a linear form. It's not very strong. And it has kind of that negative direction to it. So when we have that scatter plot paired with the correlation, what that correlation value tells us, the negative part tells us that our association is negative. The fact that it's a value not very close to 1 tells us that it's not very strong. So when we interpret it, that value of negative 0.427 indicates my linear association, and that is important. Okay, the linear association between height and free throw percentage is negative, and in this case, fairly weak. So when they ask you to interpret correlation, you want to make sure you have a graph to verify you have that linear association, and then that number will tell you both the strength and the direction of that association. Okay. The next part of this here then, correlation and causation. This is one of the biggest misconceptions that people have with this idea of correlation. And this is something that advertisers take full advantage of. The general person or the general population doesn't understand this idea of correlation. When people hear correlation, a lot of times people lead them to believe that that correlation means causation. It means there's a cause and effect relationship that we see here. The problem is, when we measure correlation, we're measuring the strength and direction of the relationship between my two variables, but I'm not doing anything to determine cause and effect between the two. So as an example, okay, a study's done at Hickory Hill Elementary. The results show that the association between shoe size and reading ability is strong and linear, with a correlation that is very close to 1. So it's a positive association, meaning as shoe size increases, so does reading ability. So the correlation would suggest a very strong association between these two variables. So if correlation and causation were the same thing, shouldn't we just buy kids larger shoes and they can read better? So if we're thinking about that, would that make any sense? No. What's most likely happening here? Yeah, if their shoe size is increasing, it means they're probably also growing and getting bigger. And when they're getting bigger, they're also getting older. And as they're getting older, they have more education, right? They've gone through more grade levels. So when we're looking at this, the two variables that we examined aren't the variables driving the change we see. So shoe size has no bearing on reading ability. The fact that their shoe size is increasing is because they're getting older. And because they're getting older, they're getting more education. That's why they're getting better at reading. So when we're looking at these scenarios and we're talking about correlation, Correlation only tells us that there is a relationship between the variables. So there is some sort of linear association between the variables. It does not mean cause and effect. What we have to think about is when we look at those two variables, could there be something else, something that we didn't measure, something we didn't look at, that's actually driving the relationship we see? So we call those lurking variables. So it's a variable that has an important effect on the relationship of the variables that we are studying, but it's not a variable we looked at. So when I go back to that example, okay, we looked at shoe size versus reading ability. So we saw the positive association, the strong linear relationship, but what we didn't account for was age and grade level. So there were lurking variables that were actually driving that relationship that we saw. It wasn't the shoe size driving the reading ability. It was something in the background that we didn't take a look at. So when people throw around this term correlation, okay, a lot of times they throw it around trying to show cause and effect. Correlation does not imply causation. It tells us there's a relationship. It has no bearing on whether that's a cause and effect relationship. That requires a much further or deeper analysis. Okay, so always be aware of those. Here's another example just to show the difference. So correlation, 100% of people who breathe die. So there's a very strong correlation. People who breathe do die. Breathing is not causing you to die. Whereas in the bottom, 100% of people who don't breathe die. So if I were to all of a sudden start holding my breath and never breathe again, I am going to die. There's that cause and effect. So it's two different ideas. So when we talk about correlation, we have to make sure we understand it's not causation necessarily. It tells us of a relationship. We'd have to go a little bit deeper to figure out what type of relationship that is. Okay. Last couple of things here. When we calculate correlation, now we're going to talk about the formula for correlation. I'm not going to have you calculate correlation by hand. We did that with standard deviation, and it was important for standard deviation because you needed to know kind of where things came from there. With correlation, just examining the formula kind of gives us everything we need. So I'm not going to have you go through and calculate correlation by hand. But I do need you to understand what the formula tells us. This reinforces some of the ideas we already discussed earlier with correlation. And so when I look at the formula here, just like with standard deviation, we notice that we're dividing by the degrees of freedom. So the number of observations minus 1. And then the Greek letter here, the sigma, means summation. So we're going to be adding the values that we calculate inside here. And as we look at the formula, it looks a lot more complex than it really is. When I look at this and I kind of break this down, when I take an x value minus its associated mean and divide by its associated standard deviation, all I've done is calculated a z-score. So whatever my x value was, I standardized it by calculating the appropriate z-score for it. And then I turn around and do the same thing for the corresponding y value. So as we look at this, what we're really looking at here, when I go to calculate my correlation, I'm taking the z-score for x, multiplying it by the z-score for y. I add all of those values together, and then divide by my degrees of freedom, divide by n minus 1. Now, the reason it's important to know this formula and know where this correlation value is coming from is this tells us two of those properties, two of those characteristics that we discussed earlier. First, if I'm doing the z-score of x times the z-score of y, if I were to flip my variables So whatever I had as x switches to y. Whatever I had as y switches to x. Is this product and sum going to be any different than my original product and sum? No. If I flip multiplication, it doesn't matter. I'm going to get the same number either way, right? So the order that I put x and y in does not matter. And that's because of the formula that we're using here. The other part of this, since I'm calculating z-scores, the minute I calculate this z-score, if x was in pounds, the minute it converts to z, pounds are gone. They're no longer relevant to the problem. If I was measuring y in hours, the minute I calculate the z-score associated with that, hours are gone. So there are no units attached to my actual calculation, which is why if I took x and switched from pounds to kilograms, it's not going to matter, because those units are going to be eliminated the minute I start calculating that correlation coefficient. So when we calculate this correlation, it's important to remember we are calculating z-scores. We're calculating standardized values. So the units get stripped. We're using multiplication on those z-scores, so it's commutative. It means it doesn't matter what order I go in. And then just like with standard deviation, we're dividing by those degrees of freedom. Okay? And again, I'm not going to make you carry out the process of calculating this by hand, but I do need you to know what that formula does. Okay? So let's talk about how to calculate correlation, but we're going to do it on the calculator. So in the following example here, so it says a certain stats teacher wants to see if there's a strong association between the number of days a student misses and the student's semester grade. He collected data for 5 of his students. We have the values in the table below. We want to calculate the correlation. Now on this example, we're actually going to accomplish 2 things here. We're going to talk about how to do a scatter plot in the calculator, and we're going to talk about how to calculate correlation on the calculator. Okay? So the first thing, if I'm going to do anything with scatter plots, anything with correlation, I'm going to take my data set and I'm going to get it put into my lists on my calculator. So this is where I have to look at, okay, when I look at my variables, I do want to make sure I identify my explanatory and my response variable. It will not matter for correlation. It will matter for the scatter plot. When I switch the x and the y, it affects that scatter plot. So when I do that, the creation on my calculator here, I need to have x in the correct location. I need to have y in the correct location. It's not important for the correlation part of things, but it is important for the scatter plot part. So scatter plots don't have the same properties, same characteristics as correlation. If I flip the variables, I will change my graph drastically. Okay? So in this case, if I'm looking at number of days absent in semester grade, which one is going to be the explanatory? The number of days absent. This is my x variable. My semester grade then will be my response. Which means in my calculator, we're going to go into the stat menu. We're going to edit. So just stat, enter. We're just going into our lists. We are going to put x into list 1, and we are going to put y into list 2. Every time we do this, we're going to put x in list 1, we're going to put y in list 2, and then when you go to a different example, you're just going to overwrite those lists every time. So get those values entered here real quick. After you enter the values, always just run a quick double check that you typed everything in correctly. Specifically with this, make sure you have the x and y values together correctly as well. So make sure you have the 9 and the 60 in the same spots, 5 and 84, 2 and 93. My x and y values have to correspond to one another. If I mix up the order of one list or the other, again, drastically alters the results. So if I have this if I have this information, if I'm going to work with correlation, we said correlation only really works if we have a linear association. So the first thing I might want to examine is, given this association, do I have a linear association to begin with? So if I want to create a scatter plot on my calculator, we're going to go into that second, and y equals, we're going to go into our stat plot menu. We're going to go into plot 1. Make sure to turn it on. And then you're going to select the very first graph option. So we had been setting these up to work with that normal probability plot. That was the last graphical option I could select. Now we want to go back to the first option. When I select that first graph option, it should ask for the X list and the Y list. Those should already be defaulted to list 1 and list 2, which is where you should have put the information for your values. So once you have the correct lists put in for your X and your Y, we're going to hit zoom, and then the number 9. Yep, so make sure to hit enter now. So you have it highlighted, but now you hit enter. Yep. Okay, and now if I need to switch my lists, so list 1 is good, but if I want the Y list to be different, if I just hit second and then number 2, because that's the list I want.
Okay.
Right there. Okay. Okay, so everybody should see their scatter plot right now. Now, as we look at the scatter plot, let's see, dimension mismatch. Oh, you got an extra value here. Now it should work. So when we look at the scatter plot there, do we see a fairly linear pattern? Okay, so it's fairly linear, right? The other thing we can get from that is direction looks to be what? Negative, and strength appears to be pretty strong, right? Now there is a point, it looked like as I was looking at people's graphs, there is a point that doesn't really follow the majority of the points, right? So that would be one maybe we examine. That might be that possible outlier we identify in the problem. Okay, so we talked about those yesterday. But that's going to be my graph. So I've established that it does appear to be linear, which means correlation would be an appropriate value to calculate. Okay, so now if I want to calculate correlation on your calculators, so go ahead and quit out. So second mode to quit out. Now for most of you, the first thing we're going to have to do here is we're going to have to turn on what we call diagnostics. And as I'm looking here, almost all of you have the easy way of doing this. So if I'm on my calculator, just the regular screen, hit your mode button. And then if you scroll down towards the bottom, so almost at the very bottom there, there's a spot that says diagnostics or stat diagnostics. You want to turn that on. So highlight the on and hit enter to select that option. Now once you do this once, you should not have to do this again. The only time you would have to do this again is if your RAM got cleared for whatever reason. So if you borrow one of my calculators, you're almost going to have to do this every time because I always clear the RAM from one class to the next to the next. Okay, so you might have to go in and turn this diagnostics on. If you have your own calculator, once you turn it on, it stays on until you turn it off. Okay? Chris, were you able to do that option? Okay. All right, so we got our stat diagnostics on. So now we go ahead and clear out of that or quit out of that. And then on the calculator to get correlation, we're going to go into our stat menu. This time we're going to calculate. And in that menu, we've got two different options that you can select. Now these options that we're selecting, this LinReg, this is for linear regression. This is going to be our topic for tomorrow and next week. But we're going to select either of the two options, and it doesn't matter right now. It's just two different forms of the equation, which is something we're going to talk about over the next couple of days. So right now you can ignore or not. It doesn't matter what the other pieces of this are. So you're going to select option 4 or option 8. Both are LinReg functions. And just like before, make sure it has list 1 for x, list 2 for y. And then when you calculate, it's going to give you an equation, y equals ax plus b, or a plus bx, depending on which one you chose. It gives you a, gives you b. Right now we're ignoring those. We'll talk about what those mean tomorrow. But then down the list, you see r squared. Again, a topic for later, so we ignore the r squared. I want the very bottom value, my r. So when I run that LinReg on my calculator, if my diagnostics are on, I'm going to see that r value, that correlation coefficient. Now, when you go to copy this down, be very careful when you're reading the correlation. If you get into too big of a hurry, a lot of times the negative sign is really easy to miss. It's pretty small in that function there. So if you're going too quickly, you miss the negative sign, because we know that in this case, it has to be a negative correlation. We saw that negative association in our graph. And so when you did that, what do we get for that correlation value? Negative 0.9, let's go with like 3 places. 9 what? 3.6. So when we give correlation values, I want you to go to 3 decimal places every time. So my correlation value would be negative 0.936. If I wanted to interpret that, so we already established that this was a linear association, so this negative 0.936 tells us there is a very strong negative association between the number of days absent and the semester grade in a class. So once I have that value, being able to interpret it in terms of direction and strength. Okay, so that's what that's going to look like. Any questions on that so far? Okay, and you'll get some practice with that on the homework, doing the correlation in the calculator. Last thing here. So final cautions. When we calculate correlation, one of the things we have to be aware of, this wasn't on that property list that we did earlier. Correlation is a non-resistant measure. Meaning what? Outliers affect it. Okay? So R is a non-resistant measure. That means if I have outliers present, I'm not going to necessarily get an accurate reflection of the overall association. So I have to be aware that outliers are going to be a problem. We already discussed R should never be a value given alone. You should have a graph of some kind that indicates we do have a linear association, because if it's not linear, that correlation value becomes meaningless. And then, as we already discussed multiple times, we do not use R, we do not use correlation for nonlinear relationships. Now, the 2 graphs that you see here just illustrate the idea of that first concept, that R is non-resistant. So as we look at the scatter plot, this first scatter plot here, when we look at the form, it's linear, positive, moderately strong, okay? But we notice that there are points that don't follow the regular pattern. For instance, this point up here. falls quite a bit off the beaten path. Now, when I see a problem or outlier like this, so if that outlier is kind of towards the middle of my data set and it's way above or way below the other values, that means that when I go to calculate my correlation, this is going to have a very low z-score for x because it's in the middle of my data set. The z-score for x is going to be very low, possibly 0, which means this is going to weaken my association overall. It's going to make my value further away from my 1. Same thing on the other side here. Now on these types of problems, like these outliers where they're out in the far side or one of the extremes, those are actually ones that are going to affect us a little bit differently. When I look at this value here, okay, this is going to have an extremely large z-score for x. Now it's not going to necessarily be a huge z-score for y, but we are a little bit above the normal or the mean for y, which means this is going to contribute pretty heavily. It's going to make that correlation appear stronger than what it really is. So when I have values that fall in an extreme direction in line with the rest, it's going to increase that correlation value quite a bit. It's going to make it stronger. Whereas if they fall off the beaten path kind of towards the middle, they're going to weaken that association quite a bit. When I get rid of those outliers, so I get rid of that point, I get rid of the other point, and I recalculate based on the new values, we can see that that correlation coefficient increases quite a bit. So now instead of a moderately strong association, we have a pretty strong association. So just recognizing that outliers have that big effect, and just remember that that correlation value is not resistant. And that's also a reason why we want that scatter plot and not just the correlation value. All right. So here are the problems that I want you to try out.